Hey guys, it's Nate. Welcome back. So in this video, it probably should be a little bit of a shorter video. Just going to do a couple of different formulations, I guess, of this vector form of Coulomb's law, and to some forms that are very, very useful when solving problems. So just a little bit of derivation, twisting, turning of this guy, but ultimately, I mean, we're still sticking with the same form. Now, if we want to consider what was said in the previous video, that our R12, let me just write out here to the side, our R12 vector, the vector actually reaching from Q1 to Q2, I'll just show it a refresher. Q1 to Q2, we defined our R2 as some magnitude R12, again some unit vector A hat 12. Which would yield your actual R12 vector. So, that's equal to this guy. Simple enough. Magnitude, direction, vector. Alright. Now, a bit of an explanation on notation. When I write the absolute value bars, it'll have the arrow. If I want to talk about just the magnitude of R12, instead of writing the bars and the hats and all this, I'm just going to write 1, 2. It'll just be without an arrow, just to show that it's just a magnitude. So if I divide it out by itself, it's going to give me 1. For example, 4 divided by 4, 1, 2 divided by 2, 1. Just some scalar divided by itself. It's just going to be 1. I'm going to use this against this guy. I'm going to multiply this guy by 1 pretty much. I'm not going to change it, because I am, just multiplying by 1. So, let's do that. We're going to multiply that all by R1, R2, as such. Now, some important things, some very, very, very interesting things start happening. Now, we already have R12, the scalar form being squared. When we have the R12 here, it turns that into a cubed. So let's just go ahead and write that as cubed. See what's going on with the R12 left over. Cubed, Q1, Q2. Alright, so all I did was take this guy, include him inside the square, cubed, because essentially this is just R12 times R12 times R12, it doesn't change anything. Now, wait a minute. We already stated that the magnitude of R12 multiplied against the unit vector A12, A hat 12, is our R vector. So this guy is our actual R vector. So we can rewrite this expression. So, this is the first very, very, very useful expression in the problems that we're going to be doing. I'll go ahead and do the dot, 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 dot. Now that we have our R12 here, we can twist it around a little bit more. Now, we know our R12 is, in fact, equal to our magnitude and our unit vector multiplied. It's also equal to something else. If we refer back to the diagram, we stated R12 arrow is also equal to R2 minus R1. We can use that. So let's go back and just write it here for the sake of not having to refer back and forth. So, as such, if we want to talk about the absolute value or the magnitude, modulus, whatever you want to call it, it'd just be that. Simple enough. Real quick, if we want to just reapply that to this guy here, it would reassume form, and I love this form. It's very, very useful. Alright, so very, very, very useful formulation of this. For instance, if we had just two charges, like in this example, we're going to throw paper down to. I mean, for instance, if we had two charges in between here, sure, we could find the force acting between them, but this becomes a little bit more useful, especially when you want to start considering more than just two charges, which is exactly what we're going to build into the next video. How can we use this to help us when we want to consider systems of any number of charges that we want to consider? So, a pretty short video, I believe, at least shorter than the others. Hope you enjoyed. Let me know what you think. Thanks for watching, and I'll see you in the next video.